Hello everyone, welcome to the Quantum Mechanics Explainer video. In this video I will be going through the Quantum Mechanics and Hybridization worksheet, which is also available in the description below if you haven't been able to check that out. If you haven't watched the Quantum Mechanics and Hybridization topic video, also in the description below, go check that out. And if you're struggling with the fundamental concepts of electron configuration, I suggest you go check out my quantum mechanics video in the AP chemistry and the college chemistry courses. They'll provide a more in-depth understanding of electron configuration because this video and the topic video is meant for students in organic chemistry with a sufficient previous understanding of electrons and quantum mechanics. So before we start, let's write out the chart that we had in the video. This will help us understand the order of all our orbitals. So let's go down to maybe 5s. And then we have D, 4D, 5D, and then we have 4F, and then 5F. And we'll make lines going through them. Something like this, going diagonally. And this will show our order of orbitals. So draw some arrows on the ends of these lines, and we'll keep referring to this chart. For the problems I suggest you get out a periodic table, you probably will need to understand or be able to refer to how many electrons are in each of these elements. And so carbon has has 6 electrons. So let's write that out. And starting from 1s to 2s to 2p, 3s, 3p, 4s, so on and so forth. Let's also define how many electrons we can fit. So in the s, we have one orbital. We'll just write orb, which each orbital, no matter where it is, can only fit 2 electrons. So let's write that down. The p orbitals, well, the p shell has 3 orbitals, and each has 2 electrons maximum, which means each p has a maximum of 6 electrons. The D has 5 orbitals, which means it could fit a maximum of 10 electrons. And the F can fit 7 orbitals. It has 7 orbitals, which means it could fit a maximum of 14 electrons. And maybe to this, we wrote ourselves a little reference sheet to be able to write down the electron configurations. So the first subshell is always 1s, and it'll fill up to the max with 2 electrons, which means we have 4 electrons left at this point. The next one is 2s, and we can also fit in 2 maximum electrons, so we have 2 electrons left, and that falls down to the last shell, the 2p, which has only 2 electrons, because that's all the electrons we have left, right? And using our shortened electron configuration, the nearest noble gas is helium. It has a slightly less electrons, so it's the next one lower. And it will have 2s2 and 2p2. And so maybe we're going to struggle with some space later in these questions, but we'll try to make the best of it. Phosphorus has 15 electrons. 15 electrons. And so our first will be 1s2, and then 2s2, and 2p6. At this point we have 10 electrons, which means we need 5 more. So our next one was 3s2, and then we have just 3 more electrons, so 3p3, and it is unfilled, 3 valence electrons, and the lowest, or the nearest noble gas, which has less electrons, is neon, and then it ends up being 3s2 and 3p3. So understand that these are both valid electron configurations. This one is just a shortened form that we sometimes use. Vanadium has 23 electrons, so let's write 23 electrons. And we'll start from the 1s2, and then the 2s2, 2p6, which means we're down 10 electrons. We need 13 more. So we'll keep going to the 3s2, and then the 3p6, which means that was 8 more electrons, which means we need 5 more. And then 4s2, and 3d3. And the noble gas, which has slightly less electrons than vanadium, is argon. And it ends up being 3d3 4s2 for the shortened electron configuration. Sb has 51 electrons. And so we'll start with our 1s2, and then our 2s2, and 2p6, and then 3s2, and 3p6, which means at this point we're down 18 electrons, so we need what, 33 more, I think? I'm kind of bad at math. Then 4s2, then 3d10, we can fit 10 electrons in this d orbital. That's our first d orbital in this example. And then the next one is 4p6, and 4d10. And if I've counted correctly up until this point, we only have 5 more. So we'll write outside the box for this one. 5s2, and then 5p3. And the lowest, the highest noble gas, which has less electrons than Sb, is krypton, Kr. And minus those electrons, it ends up being 4d10, 5s2, and 5p3. The next example, Sm, samarium, has 62 electrons. It's quite a big atom, part of your lanthanide and actinide series. So we'll start with 1s2, and then 2s2, 2p6, 3s2, 3p6, then 4s2, 3d10, and then 4p6, 5s2, 4d10. And if I've counted correctly at this point, we should be 14 electrons short. So we're going to keep going with 5p6 and then 6s2. And our last two, we should have 8 electrons left, which means we have 4f2 and then 6s2, which means our largest noble gas, which has less electrons than Sm, is xenon. And it ends up having 4f2 and 6s2. Nitrogen, kind of a little break from the big elements that we've had in the past maybe 2 examples, has 7 electrons, which means we'll start with a 1s2, and then the 2s2, and this is 4 electrons, which means we need only 3 more, and so we'll have an unfilled 2p orbital, and the greatest noble gas, which has less electrons than nitrogen, is helium, and it stays with 2s2 and 2p3. The next element, silicon, has 14 electrons, and so let's start with the 1s2, and then the 2s2, 2p6, 3s2, and then the 3p2 is our final shell, and the largest noble gas, which has less electrons than silicon, is neon, and it's left with 3s2 and 3p2. Fe, iron, has 26 electrons. 26 electrons. And we'll start as usual with 1s2, and 2s2, 2p6. That's 10 electrons. We need 16 more. 3s2, 3p6, and that leaves us with 8 electrons left. And we'll keep going to the 4th shell, which is 4s2, and the final shells that we have left is the 3d2 shell and the 4s2 shell. And the largest noble gas, which is smaller than iron, is argon, Ar, and we are left with 3d6 and 4s2. The next element, Te, has 52 electrons. And so we'll start with the 1s. So 1s2, 2s2, 2p6, and the 3s2, 3p6, 3d10, 4s2, 4p6, 4d10. And at this point, if you count, we should be short 6 electrons. So the last two shells that we have is 5s2 and 5p4. And the largest noble gas that has less electrons than tellurium is krypton, which leaves the shorthand electron configuration 4d10, 5s2, and 5p4. The next element, terbium, Tb, has 65 electrons, so quite a long one. And we'll start with a 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and then we move on to the 4f9, 5s2, 5p6, and our final shell 6s2 is completely filled. And the largest element, largest noble gas, which has less electrons than terbium, is xenon. And so the shorthand electron configuration is xenon 4f9, 6s2. Our next element is not really an element at all, it's an ion. We have nitrogen with a -3 charge. Pretty interesting. And so nitrogen with a -3 charge, what we can do is regular nitrogen, well, it has 7 electrons. But since we have a negative charge, we're going to add 3 electrons to that, which gives it 10 electrons. And so maybe a little shortcut, I mean, we can just look at our nitrogen example from before, but let's just rewrite this, right? And so we'll have 1s2, 2s2, and then we're left with 6 electrons, and the 2p can take all of those remaining electrons. Our largest element, which has less electrons than nitrogen, is helium, which ends up 2s2 and 2p6. Calcium, regular calcium, has 20 electrons, but since we have a +2 charge, we can take 2 from that, which means we have 18 electrons in the calcium ion. And so we'll start with 1s2, 2s2, 2p6, 3s2, and their last 3p6. And it ends up being the same electron configuration as the noble gas argon. Pretty interesting. And so our shorthand is literally just argon. The next example is sulfur with a -1 charge. So regular sulfur has 16 electrons. I'll just write 16. But since we have a negative charge, we can add 1 to that since it gained an electron. And we'll make that 17 electrons. And we'll write the electron configuration for that, which is 1s2, and then 2s2, 2p6, and then 3s2, and should come down to 5 electrons left, which is 3p5. And the largest noble gas with less electrons than sulfur is neon, and it ends up with 3s2 and 3p4. The next example is cesium with a +2 charge. So it ends up with regular cesium has 55 electrons, but since it lost 2 electrons, we could give it really just has 53 electrons. So we can start writing the electron configuration as 1s1. Let's fix that a little bit. Then 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d10, 5p5. That ends up our electron configuration examples. The next question is asking which atom has the electron configuration given. And if you were to add up, so to solve this question, an easy way is just to add up all the electrons. So 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 2. We end up getting 40 electrons. 40 electrons. Which ends up that according to our periodic table, this electron configuration belongs to zirconium, or Zr. So let's just write that out, Zr. The next question, a similar question, if you were to add up all of these, so 2 plus 2 plus 6 plus 2 plus 6 plus 7 plus 2, you end up with 27 electrons, which means our element is actually cobalt, or Co. So let's write that out, Co. Which ion with a positive 1 charge has the electron configuration below? Positive 1 charge means that it lost an electron. And so if we count this up and then just add an electron, we'll be able to find the original element and then just add a positive 1 charge. And so if you add up 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 6, you would end up with 36 electrons. But since we lost an electron, this is a positive 1 charge, we can add 1 to it, which gives us 37 electrons. And so the original element was actually rubidium, or Rb. And so I'll write rubidium positive 1, or Rb. Oops. Rb positive 1. The next question is similar. Which ion with a negative 2 charge has the electron configuration given? And so this is an ion that gained electrons. And so if we count this up and just subtract 2 from it, we'll find the original element that this is asking for. So if we add 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 6, we'll end up with 36 electrons. But since we gained electrons, we'll subtract minus 2, which means 34 electrons. And so the original element was actually selenium. It just has a negative 2 charge, selenium. Negative 2, or Se. Negative 2. The next question, which principle or rules must be used to determine the correct electron configuration for carbon in its ground state? And so if we're reading them, this is literally from the video, the topic video, but we stated all of these, right? We stated Aufbau, Hund, and Pauli when doing our electron configuration for carbon in the video. And so, well, we need all 3 of them, and E fits our answer choice. The following electron configuration represents, and so you'll see something interesting, right? This is not like the arrows that we have in the videos. We actually have hybridized orbitals, or so they say, right? And if we look at it, this might seem, oh yeah, hybridizing. You might be tempted to pick this question. But if you realize it, why is this orbital 2sp3? That means that too many orbitals fuse together to produce hybridized orbitals. It should end, only these orbitals should have been fused to create the hybridized orbital. And so the correct answer is actually E. It doesn't really make sense in this question. Number 8 is asking us similar question. So again, we have hybridized orbitals. That erased the previous answer. And if we were to count it up, we would actually get 6 electrons. And this makes sense, right? We have 1, 2, 3, and then fourth orbital with the proper number of electrons. And so this is the sp3 hybridized state of carbon. This question is asking us to select the hybridized atomic orbital. And so if you watch the previous video, you'll be able to see the shapes. I posted a picture in one of the slides of the changes in shapes that hybridized atomic orbitals go through. And so the only visibly hybridized atomic orbital is the 3rd one. This one looks like a regular s orbital. The rest are, I don't know, just little circles. Not exactly sure what they could mean, but the third one is definitely a hybridized orbital, and so this is going to be our choice. The next question is asking us how many sp3 bonds are there in the following substance. And so you might be confused, well, what is this really asking me? But realize S probably means we have hydrogen, right? In this structure, we only have carbon and hydrogen. And so it probably is asking you for hydrogens bonded to sp3 hybridized carbons. And so first, well, let's circle all our sp3 hybridized carbons because we cannot have any sp2 or sp hybridized carbons. So these are the only ones we have. And maybe in blue, we'll draw out lines to show how many hydrogens we have. So we have 3 on this one, then 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So then that means that we have a total of 13 sp3 bonds in the following substance. And the next question is asking you something almost the same, but a little different. And so S probably again means hydrogen, and sp2 just means sp2 hybridized carbons. And so we should go ahead and maybe circle all our sp2 hybridized carbons. So we only have 4 of them. And then we'll draw out how many hydrogens we have connected to these carbons. So we have 1, 2, and 3. So that means we only have 3 sp2 bonds in the structure. In this question, they're asking us to identify the atomic orbitals in the carbon-carbon bond in the molecule below. So if we just maybe draw out a Lewis structure for this, we'll be able to see that each of these carbons have 2 regions, which means it's sp2 to the power of 2 minus 1, 2 regions each. So sp1, or we could just write it as sp. And so this is an sp hybridized carbon as well as an sp hybridized carbon, this one. And so the only answer choice that really fits it is C, because we have 2 sp orbitals interacting with each other to form a triple bond. In the next question, it's asking us something almost the same. So let's redraw a similar structure. But this time it's asking us for the carbon-hydrogen bond. And so let's choose, for example, the left side. This carbon is again sp hybridized, and this hydrogen just has an s orbital. It only has 1 electron. And so the only answer choice that really fits this is 2sp and then 1s, which is E. The next question is asking us, what is the hybridization of carbon indicated with the arrow? And you might be thinking, well, we didn't discuss carbons which have positive or negative charges in the video, but it's all the same, right? Using the rule of hybridization equals sp to the power of regions minus 1. Well, let's just count how many regions we have. So we have 1, 2, and 3, and since it has a positive charge, there are no lone pairs, which means that the hybridization is sp to the power of 3 minus 1, meaning that it has an sp2 hybridization, which is answer choice B. Which the following contains an sp2 hybridized carbon? It's kind of funny, this answer choice is right after the one we just did. It's CH3. CH3 is the only answer choice that has only 3 regions. And so if we count these, 1, 2, 3, it ends up being sp to the power of 3 regions minus 1, which is sp2 hybridized. This question is asking us, what is the approximate hybridization state of the oxygen atom in C2H5OH? And so let's maybe draw this out in a bond line structure. Looks like something like this. Or in general, we can maybe zoom in onto the oxygen and show that it also has 4 regions. 1, 2, 3, and 4. That's 4 regions, meaning that it's sp to the power of 4 minus 1, which means it is sp3 hybridized. So it is approximately, it's not really, because the sp system is a little better, mainly for our carbons, but it goes, right? It's almost sp3 hybridized. And the next question, what is the approximate hybridization state of the nitrogen atom? Well, let's maybe draw it out. So we have 3 methyls attached to nitrogen, and nitrogen will have a lone pair. Remember our honk mnemonic. And so if we count how many regions we have 1, 2, 3, and then 4. Once again, we have 4 regions. And so it's sp4 minus 1. So it is approximately sp3 hybridized. Again, not exactly like carbon, but almost very similar to carbon. The next question is asking us to identify the hybridized orbitals involved in the C2 to C3 sigma bond. And so if we were to, we don't really know what a sigma bond is yet, but we'll discuss that in the next video. For now, we don't need to know what it is. They're telling us that it's a C2-C3 bond. And so we'll write that, well, this carbon is C2, and this carbon is C3. And so if you notice, this carbon is triple bonded to another carbon, which means this is sp hybridized. But this carbon has a double bond, which means this one is sp2 hybridized. And the best answer choice that fits that is E, sp and sp2. The next question is asking us which molecule contains an sp hybridized carbon. Well, I would look at it right away and just realize, well, HCN is carbon triple bonded to a nitrogen, if you were to draw that out. But if we were to prove ourselves, well, we only have two carbons, which means they are both sp2 hybridized. This carbon has 4 bonds, should be all signal, which means it's sp3 hybridized. This carbon has a double bond and 2 single bonds, which means it's sp2 hybridized. And all of these carbons have, in the last example, have 4 single bonds, which means they are all sp3 hybridized, leaving us with answer choice F. The next question is asking us to identify the atomic orbital the lone pair electrons on the carbon are contained in. And so you might be confused by this, but let's just count how many regions we have. We have 1, 2, and then 3. And so if we were to figure out the hybridization of this weird looking carbon, we would get sp2, which means that all of our bonds actually, including our lone pair electrons, are in sp2 hybridization, which means the only valid answer choice is B. The next question is very similar. If we count how many regions this nitrogen have, we'll figure out that we have 3 regions. And so if we use our formula, 3 minus 1, sp2 hybridized, the only valid answer choice is A, sp2 hybridized. The next question is asking us a very similar question. And so if we were to count the regions again, we would figure out that we have 3 regions. So 3 minus 1, we have an sp2 hybridized nitrogen. So the answer choice should be D. The next question is asking us to find the hybridization for each of the carbons in this molecule. And so let's go ahead and carefully figure this out. This carbon has 2 single bonds and a double bond, which means it is sp2 hybridized. This carbon has a double bond and 2 single bonds, which means it is also sp2 hybridized. And if you look in the rest of the example, every single carbon is literally the same hybridization. And if you haven't realized this yet, this is a benzene ring. If you haven't touched on that yet in organic chemistry, don't worry. You will for a whole chapter, very later, much later in the course. But all of the carbons in this ring are sp2 hybridized. The next question is asking us for the hybridization of the carbon atoms of the molecules below. And so a useful thing is to maybe draw out lines to show hydrogens connected to these carbons. The only 2 carbons are this one and this one. And so this carbon has only single bonds, which means it is sp3 hybridized. This carbon has 2 single bonds and 1 double bond, which means it is sp2 hybridized. The next example has only 1 hydrogen connected to each of the carbons, and each of the carbons have a double bond on one of the sides. And so all of these carbons are sp2 hybridized, similar to the benzene question we had before. And so let's fill that up. sp2 and the last carbon also sp2 hybridized. The next question, well, this terminal carbon has 3 hydrogens attached, which means it has 4 single bonds, meaning it is sp3 hybridized. This carbon right in the middle has 2 single bonds and a double bond, meaning it is sp2 hybridized. The next question is asking us to propose structures for molecules that meet the following descriptions. A contains 2 sp2 hybridized carbons and 2 sp3 hybridized carbons, contains only 4 carbons, all of which are sp2 hybridized, and contains 2 sp hybridized carbons and 2 sp2 hybridized carbons. So let's start with A. we need 2 sp2 hybridized carbons and 2 sp3 hybridized carbons. And so the structure I drew actually looks like this. If you realize, well, these in blue are sp3 hybridized carbons, and these 2 carbons are sp2 hybridized. But we can actually just move this double bond, and it would work as well. Now these 2 end up sp3 hybridized, and the endings are sp2 hybridized, and I do not have to draw a separate example with flipping the double bond on this side, because it ends up being the same molecule. But we'll learn about that a little later in the video about isomers. In B, it's asking us to contain only 4 carbons, all of which are sp2 hybridized. Well, the only way to really do that, let's draw a similar structure as before, is to make sure that every carbon has only 1 double bond. And so this is the only way to really draw that. There might be different, aesthetic ways to draw that, but this should be the only way, with a double bond, a single bond, and a double bond. The next question is asking us to propose a structure that contains 2 sp hybridized carbons and 2 sp2 hybridized carbons. So you can really draw anything, right? Draw whatever your mind, commands you, but we can start with drawing our sp hybridized carbons, because it really should just be a triple bond, and then somehow sneaking a double bond in there. And so this ends up with 1, 2, 3, 4 carbons. And so this is the only way to really draw 2 sp hybridized carbons and 2 sp2 hybridized carbons, and this is C. The next example is, what do you expect for each carbon atom in the following molecules? And so we'll write, well, this one has a double bond, so sp2, another double bond, sp2, double bond, sp2, double bond, sp2, double bond, sp2, almost like a little wrap, double bond, sp2. This carbon also has 1 double bond, so sp2. This carbon has 4 single bonds, so it is sp3 hybridized. This carbon also 4 single bonds, so it is also sp3 hybridized. Each of these carbons, even though they have different number of hydrogens, are all only single bonded, so they have all sp3 hybridization. And so that is procaine. I believe it is a type of drug or something. I'm not exactly sure. The next question, this carbon has 4 single bonds, even though they're not drawn. So this is sp3. This carbon, very visually, well, sp3 hybridized. This carbon also 3 single bonds, so sp3. This carbon only, 1 double bond, so sp2. And both of these have double bonds, so it is sp2, and this one is also sp2. That concludes the worksheet on quantum mechanics and hybridizations. If you're feeling troubled by this topic, check out the topic video in the description below, and I will see you guys in the next video.